Hello everyone, welcome back to Diksha Karnataka YouTube channel, and I wish you a very happy new year to all my students, my friends and everyone who are watching this video. Obviously you are my friend as well, right? Now today I am going to discuss a very important chapter from your second PU, which is current electricity. So in the Decode NCERT series, we are trying to help you how effectively you can read from NCERT along with the lectures that we have done. If you read the NCERT, it will be a complete package. You will be assured of scoring 99% even out of out, right? So that's why we have started this series. Our sole motivation is to make sure that you achieve your dream of getting this out of out in physics, which seems very difficult. Actually not. Now in the chapter current electricity, before I go into this chapter, I have a small announcement that you know that we have launched PU2 Success Blueprint Test Series, and currently we are going to have the fourth pass test on this Sunday. And currently there is an offer going on. If you purchase this product now, you will get a flat 100 rupees off. So the actual product of the product price is 599 rupees for physics, chemistry, maths and biology or CS. But if you add my coupon code SAM all caps 100, you will get a flat 100 rupees off. So you will get everything for 499 only. This is a new year gift from my side to all of you who wants to participate in this test series. The detailed about this test series is already discussed in a separate video, so do watch that if you are still confusing that whether you should buy it or not. Now let's start with this chapter. So first chapter, in introduction part, you can skip everything. Nothing is important there. In this part from the second page of the chapter, you can see there I have highlighted few parts. So current is basically the definition of current, the formal definition of current. You have not given the formal definition of current as of now, so this is the first time you are getting the formal definition. So sometimes they might ask what is the electric current. Maybe in some form or another you might face this question. So maybe you are teaching your brother who is younger than you. So then you have to know what is electric current is. Electric current is charge per unit time, is defined as charge across the area forward direction. If it is turned out to be a negative number, it implies that a current is in the backward direction. So this is very important. If current is negative, that means if you assume that current is flowing say in this direction. Suppose you assume that current is flowing in this direction, and after all the calculations you found that current turns out to be negative. In that case, what is the meaning of the negative current? Negative current means that in reality the current is actually flowing in the opposite direction. Okay, so if the current in this direction is positive I, then current in this opposite direction is negative I. That's it. Okay, as simple as that. And there is one more definition of current which you may be useful in some competitive examinations, that current is also defined as the limit of delta Q by delta T. And what is this? Delta T tends to 0. What is this? You know this answer. This is nothing but dq by dt. Okay, you can write dq as capital Q or small q, does not matter. Okay, basically it is dq by dt. So basically current is the time derivative of the charge. In some cases there will be given a function of charge as a time, charge as a function of time. So in that case, if they ask you to find what is the current, then you have to do the differentiation of the charge to find the current. That's it. Okay, this is the another part. Other than that, you can mostly skip all of them. If you want, you can read them once, but they are not super important. Okay, even these parts also are not super important. I have seen students wasting too much time. Don't waste too much time in all this. You can come back and start from Ohm's law. Okay, Ohm's law is the most important law from this chapter. Okay, and as you know, voltage is directly proportional to the current, and if you remove the proportionality constant, it becomes V is equal to IR. So that is the Ohm's law, and in this book they have mentioned RI, which is same. Okay, here R is called the resistance of the conductor. The SI unit of resistance is ohm, and it is denoted by the symbol of omega. Okay, the resistance R not only depends on the material of the conductor, but also dimensions of the conductor. We will see that in a while, how it is dependent on dimension and material of the conductor. So you can skip everything, and this is the summary. This part you can remember, but eventually everything comes down to this single equation. Okay, in the past, long time ago, they used to ask you what is the relationship between length and resistor, and hence prove this, or hence define the resistivity. So that time is gone. They will no longer ask you individually these two relationship. They will directly either ask as application questions of this formula, or they might ask what is the relationship between length, area, and the material. Directly they will ask this question. So that is the formula that you have to remember. R is equal to rho L by A. L is the length of the conductor, A is the area of the conductor, and the constant of proportionality rho depends on the material of the conductor but not on the dimensions. Okay, rho is called resistivity. So rho is resistivity, and using the last equation, Ohm's law, we can write this as V is equal to IR, or I is equal to rho L by A. Okay, so rho L by A, we have put the value of R over here, and we have to do some little bit of simplification, and after doing the simplification we arrived at J equals to sigma E. What is J? J is basically a new term, is called current density. What is current density? Current per unit area. So J is basically current density, and it is equals to I by A. Okay, this is called current density. Current density, unit of current density is very important in terms of objective questions. Obviously you can see it is ampere per meter square, or ampere to the power minus 2. So because current divided by area, current is ampere, and divided by area means meter square. So divided by meter square, which turns out to be meter to the power minus 2. Right? So this is the unit of current density. Current density is not ampere per meter cube, like we have seen in case of normal density. Meter cube is meter to the power minus 3, or cubic per cubic meter is the most common unit, but in case of current density it is a surface density, right? So that's why its unit is ampere per meter square. So that is what important in this case. Okay, and this is a form of Ohm's law. J is equal to sigma E. In one old KCET paper, they asked you which of the following expression is Ohm's law. So they have given different relationship, and out of that J is equal to sigma E is one of them, and I think no, they gave you E is equal to J rho. So E is equal to J rho was the correct formula. So these are the forms that you can remember. E is equal to J rho and J is equal to sigma E. Okay, these are the two forms of Ohm's law. Both represents Ohm's law, and this term sigma is called conductivity. Okay, conductivity is how conductive a material is. So resistivity is how resistive a material is, how much resistance it provides. Similarly, conductivity is the quantity which defines how good a conductor is. Higher the value, higher it is the good conductor it is, right? So this is the new term. This is also Ohm's law. Okay, sometimes they might ask you that derive this equation. Maybe very often it has came, but you can remember this derivation as well. Now next, another important concept, drift of electrons and origin of resistivity. So as you know that if we put an electron in the electric field, okay, then, and mass of the electron is m, then it will have a acceleration of E by m, right? So force is, electric force is E times small e times capital E. Why? Because force is QE, right? If you remember in the last two chapters, both chapters we have discussed that force acting on a charge is basically given by Q times C, right? Force equals to Q times C, and here in this case Q is minus E, negative of E, because it is an electron. So charge of an electron is minus E, and suppose the applied electric field is E, then this is the force acting on it. Now from Newton's second law, we know that force is nothing but father equals to ma. Father equals to ma. From there you can calculate the acceleration, minus E by m, right? So this is how you can calculate the acceleration. Just for some competitive examinations, this formula might be handy if you know it, but you can find it as well if you know the relationship between force and charge, so that is also fine. So just to brush up your mind in case you may forgot, so just to give you an idea what is the how this is coming. Okay, now the tau, there is one more term in which is important here, that is tau. Okay, it is like small t. We know we have used the same symbol for torque. So this is the torque, but this is without any vector symbol, only normal tau. So tau is the time average between the successive collisions. So as we know that electrons are accelerating, they are colliding with each other, right? So the accelerating electrons, they are colliding with each other, and between two collisions, okay, electrons can collide in a random way. Even if you have applied some electric field, okay, the collisions are random, and the time difference between two collisions is not fixed. So what we have to do, we have to find the average time, right, which is more important. So to find the average time, we have defined a term called tau, which is the average time difference between two electron collisions. So when the electrons is moving in the conductor, so basic idea is that when the electron is moving in a conductor, it collides with the neighboring electrons, right? So when you are moving in your college, or entire college say is full with the students, and you want to move from one end to the other, and then what you have to do, you have to collide with your friends. Arey, keep left, keep right, like that, right? So you have to collide with them. Or if you are if you want to visit a concert going on somewhere, and if it is full, you want to go in the front, so you have to collide with everything. So electrons are like that. They are like just like you. They want to collide, and they want to go to the other side. They want to see what is on the other side. So when they are moving, they randomly collide with all the other electrons present in the neighborhood. So during the collision, between the two collisions, there is a average time delay. That average time delay is called the tau. There is a name for that, we will see that in a while. So the name for that is called relaxation time. So when the electron is getting collided, that means it is not relaxed. But when the electron has collided and another collision is coming, between two collisions the electron is relaxed. So that's why it is called relaxation time. The term for tau is called relaxation time. It is important to know that there is a quantity called drift velocity, which occurs only when there is a external electric field present. So in the presence of external electric field, the electrons start drifting from one side to one side of the conductor to the other side of the conductor. So in that case, what happens is that opposite direction of the electric field, basically we know that negative charges move opposite to the electric field, positive charges move in the direction of electric field. So electrons move opposite to the applied electric field. So that velocity with which it moves is basically kind of constant. Even though it starts accelerating, it stops because of the fact that in between two collisions it is not colliding. So because of that, you can calculate the drift velocity, which is very, very important, right? So the drift velocity is given by E tau by m. So this is a small derivation, not often asked, but you can remember it, okay, based on this. Some competitive exam questions have came in the past. So you can understand the concept of drift velocity from here, right? So this is the concept of drift velocity. Only the definition is important. Now there is one other derivation, that is I is equal to NEA VD. Okay, so NEA VD, this also used to come in the derivation part, but as you can see in this current scenario, there the derivation is not clearly stated. Okay, but it is very easy derivation. If you read this paragraph, okay, there they have said how they have arrived at this equation. So this part you can check, okay, but according to my suggestion for your PU board exam, okay, the formula is more important rather than this derivation. Okay, so I equals to NE area A VD. Okay, you have to remember this formula. And they will often ask what is the relationship between drift velocity and current. Also they will ask explain the terms. So you have to know what is N. N means number density, E is the charge of an electron, A is the area of the conductor, VD is the drift velocity. So this is the current expression for current, very very important. Okay, based on this there is another derivation of the formula, that is J equals to NE square by M tau into E. Sometimes this used to come, this is also not coming, because from this chapter 3 marks questions are not coming. In all 3 blueprints only 2 marks questions are coming. So only the formula is important and its terms are important. Okay, N is number density, E is charge of an electron, here M is the mass of an electron, and tau is the relaxation time, and E is the applied electric field. So this is also you have to remember, these formulas are important for your exam purpose. Now let's move on. You can see the conductivity is also defined NE square M by tau. This is also another important formula for competitive exam, for board exam. Okay, they might ask you what is the relationship between conductivity and the relaxation time, and write the relationship, explain the terms. So that is also another important formula. Okay, the terms I am explaining it once again. This is conductivity of the material, this is number density of electrons, this is charge of an electron, M is the mass of an electron, and tau is the relaxation time. Okay, number density means number of electrons per unit volume, and it depends on the different what is the material you are using, what is the temperature you are using. So based on that the number density can vary. Okay, so number density is kind of a constant for a given material at a given temperature. Okay, now mobility. So again another important term, mobility is how mobile an electron is. Mobile does not mean your mobile phone. Mobile means how quickly or how agile an electron can move. Okay, so the mobility is defined by VD, modulus of VD divided by electric field. Okay, and its unit is meter square per volt second. The dimension is also important, but the unit is also important. There was a question based on the dimensions of mobility, maybe in your question paper, model question paper, they have given the dimension, but in the exam they asked about the unit. So be careful, you have to be careful about the unit of density, mobility. Okay, so it is meter square per volt second. Okay, so that is important, and it is about 10 to the power 4 of the mobility in practical units. Okay, is centimeter square per volt second. Okay, centimeter square per volt second is basically 10 to the power 4 times meter square per volt second, and practically centimeter square per volt second is more often used, because meter square per volt second is very small. That is the one thing. And then drift velocity can be related as E tau E by M. So this one you already have seen. This is only the value without the sign. So the same value we have seen in the past as well in the drift velocity part. So the same equation they have given, and then they have defined that mobility is basically E tau by M. Okay, so mobility, as you can see, is a constant term. It depends only on the relaxation time of the material, right? So it is the average collision time of electrons. So this is a constant for a given material. Mobility is generally constant. Now limitations of Ohm's law. Ohm's law is not universal. There are some limitations of Ohm's law, very very important. First line is they have mentioned that V ceases to be proportional to I. So initially when V is proportional to I, you get a straight line graph. So this dotted line represents an ideal conductor, ideal ohmic conductor. So if you increase the current, the corresponding voltage will keep on increasing in a straight line fashion. But after it, if the temperature of the conductor changes, then after some time what happens is that this graph slowly it is no longer proportional to V, is no longer proportional to I. Okay, so they have they have mentioned that in a short way that V ceases to be proportional to I, but they have not mentioned the corresponding reason. The main reason is that this happens because of the increase in temperature. So if you are following using your book, you can mention that increasing temperature is one of the reason. Okay, increasing temperature is one of the reason. And the relationship between V and I depends on the sign of V. Depends on the sign of V means whether V is positive or negative. Based on that, the value of current can change. So one of the such example is a diode. So the example is given here. We have already discussed in our Brahmastra series, and again we will discuss in our semiconductor chapter, because this kind of graphs etc. we have not discussed in detail in our Brahmastra series. We have discussed a bit in our KCET series. Again, while discussing the chapter in Decode NCERT, we will see this graph again. So this is a forward bias, this is a reverse bias graph for a diode. So depending upon whether the graph is whether V is positive or negative, the value of I changes differently. So that is one reason. So basically, Ohm's law is not valid at higher temperature. Ohm's law is not valid for devices like diode. And one more limitation they have given is that the relationship between V and I is not unique. So that means for a given value of V, you have two different values of I, or a given value of I, you have two different values of V, which is interesting, right? So suppose in this case, as you can see, there is a single I and you have two different V's. Okay, this is the I. For this single I, you have two different V's. Right, so which is very unfortunate. Ohm's law does not state that. Ohm's law says that for every given value of I, you will get only one value of V, which is not in this case. So that's why in this case Ohm's law is not valid. Right, so these are the cases, and this is for gallium arsenide. Okay, so for gallium arsenide, for semiconductor devices as well as some other electronics devices, Ohm's law is not valid. So Ohm's law is not valid when the temperature is changing. Ohm's law is not valid for semiconductor devices. So two limitations of Ohm's law. Another limitation you can mention that if the state of the material changes. So for example, you are passing current through a solid wire. Suddenly, due to some heat generation, the wire melts, so and it becomes liquid. In that case, Ohm's law is also not valid. Okay, so in that case also Ohm's law not valid. Ohm's law is valid only when temperature and the other physical conditions remain same. Other physical conditions means the state of the material. So temperature and other physical condition is the one thing, and another thing is special materials. For example, gallium arsenide, diode, then triode, or transistors. Okay, in those cases this is not valid. Now resistivity of various materials. So they have given you different devices have different resistivity. That is fine. No, you can just read it once, not super important. Temperature difference or dependence of resistivity. Yeah, so this is a formula. This is a formula that you have to study. Okay, rho T is equal to 1 plus this formula. Based on this formula, there are some objective and numerical questions sometime comes for your competitive exam. I have not seen a single question from this concept in your board exam. So for competitive exam, this is important concept, that resistivity is dependent on temperature, and here this term alpha is called the coefficient of resistivity. Right, this is called coefficient of resistivity. Right, so this is called coefficient of resistivity. This is also an important equation for all the competitive exams. Okay, and one more tip is that in case they ask you, in some cases maybe you will find that instead of resistivity they have asked a question based on resistance. The same formula goes for resistance as well. RT is the resistance at a temperature say T degree Celsius. Okay, and R0 is the temperature at room temperature, or say at 0 degree Celsius. Okay, equals to R0 times 1 plus alpha final temperature minus initial temperature. Okay, so T0 is the initial temperature. It can be room temperature, it can be 0 degree Celsius. Okay, if the examiner wants a simple question, then might give you 0 degree Celsius, so that T0 becomes 0. Okay, you can apply centigrade scale here, you can apply Kelvin scale here, does not matter, as you can see that there is a difference. So even if you are using centigrade scale, does not matter. 273 you have to add in both cases and they will subtract anyway. So this formula is valid for centigrade scale as well, even though in the equation they have mentioned the Kelvin temperature, that is capital T means Kelvin temperature, right? But you can use the centigrade scale as well, because this is represented as a difference, right? There are few temperature graphs are given. Okay, I have seen one question based on these graphs. Okay, resistivity of the copper as a function of temperature T, temperature dependence of resistivity of a typical semiconductor. For a semiconductor, as you see that as you increase the temperature, its resistivity decreases. This is one of the material and example where the resistivity decreases as you increase the temperature. For normal materials, for normal conductor, as you can see, the resistivity of copper, it increases with the temperature, and some materials have, for example, here we have a nichrome wire, its resistivity varies very slightly. Okay, so because they have expanded the scale 0.10 to 1.1 to 1.2, so the value changes very slightly. Okay, so for nichrome it's almost constant with temperature. For copper it changes drastically with temperature. For semiconductor it decreases with temperature. Okay, only for semiconductor it decreases with temperature. For all other materials it always increases. But for some alloys like nichrome, the increase or change is very small. Okay, so resistivity almost remains constant. So this is the fact of about these three graphs. So if you understand that, then this is fine. The graphs are maybe important for competitive exam. I think I have seen one KCET question based on this, and the concept that I told you, based on that, objective questions, MCQ questions might come in your exam. For which material the resistivity is almost constant. They give you copper, they give you silicon, they give you germanium, they give you nichrome. So you have to choose nichrome. Or they ask you for which material the resistivity decreases with increase in temperature. So you have to choose either silicon or germanium, whatever is given in the option. One of them will be given, not both. Okay. Now let's see. Unlike metals, the resistivity of semiconductor decreases with the increase in temperature, etc. So these formulas are not important. Okay. Electrical energy, power. So this is also another important concept. I think you have learned about this in your lower classes. So electrical power is given by I square R. In your lower classes you started with Joule's heating formula, H is equal to I square R T. Then from there you came to power. First you started studied about heat energy. Then from there you have divided it with temperature time. Then you said this is that power. So electrical power is how much energy is being consumed by the device in unit time. So that is the power. Right, power means capacity to do work in unit time. Similarly, how much energy is being consumed by your household device or your electrical equipment in unit time. So that is electrical power. It is defined by I square R. Alternatively, you can use the formula V square by R. Very simple, easy formulas. It is the chemical energy of the cell which supplies the power for as long as it is can. So who supplies the energy or power that is dissipated in a resistor? So there may be a objective question. The energy dissipated in a resistor is supplied by. So there may be one objective question that might come from this line, that energy dissipated in a resistor is supplied by number 1, number 2, number 3. So that correct answer will be chemical energy. Okay, so chemical energy of the battery is getting converted into the energy that is being dissipated in the resistor. And one more formula which is my favorite formula, power is equal to vitamin. Okay, VI, Vodafone Idea, whatever you want to remember. Energy is VIT, so energy is vitamin, and power is VI. Okay, so that is how you can remember it. And one more important concept, this concept is you can skip it. One more important concept is that the power that is supplied to your household for long distance transfer of power, okay, they try to keep the voltage very high and the current very low. Okay, so this is one of the reason they have explained it, that if you keep the voltage very high, okay, resistance you cannot control. Resistance, there will be some sort of resistance even if you are using any conductor, okay, any good conductors. Obviously you cannot use expensive conductors. There used to be expensive conductors to conduct electricity, but they used to cut the power cable and they went home. Copper cable used to be used in older times, okay, during the first time when the electricity came in India under British rule. So people used to cut the copper. Copper was costly, so people used to cut the copper and take that home. So that's why there will be some resistance, because nowadays we are using iron wires, right? So resistance will be there, and because of that resistance you cannot reduce the resistance, but you can increase the voltage. This is one of the formulas that is used, and you can reduce the increase the voltage. Increasing the voltage will reduce the current, so that means you can reduce the power consumed in the circuit. Power consumed when it is traveling from the source to your home, which is maybe 300, 400, 1000 kilometers away. Does not matter from where it is coming. So if you increase the voltage, the power consumed can be decreased. So this is one of the concept that you can learn from here, that is also important for objectives. Now next is combination of cells. Let us move quickly. So combination of cell, the EMF that we say voltage, okay, EMF is nothing but the voltage. Okay, so EMF is the symbol for EMF is epsilon, and one formula, that is the terminal voltage. Terminal voltage across a battery is basically given by epsilon minus IR. I is the current in which the battery is sending current. Here small r is the internal resistance of the battery. Every battery has some internal voltage. Okay, that's why when you try to measure the voltage of a battery, you don't get the exact value that is mentioned in outside the battery. This is the terminal voltage. Based on how much current you are drawing, the terminal voltage will vary, right? So the current in the circuit can also be written as I is equal to epsilon divided by R plus R. Here R is the external resistance, external device which is actually burning the energy, and small r is the internal resistance. Now cells in series and parallel, very important, especially cells in parallel. Cells in series is basically you have connected the cells in series as well as the resistance in series. Simple. Okay, so epsilon equivalent, epsilon is equal to epsilon 1 plus epsilon 2, and R equivalent is equal to R1 plus R2. Okay, this is a very simple derivation. You can check the derivation, and it never came in the board exam, by the way, but based on this sometimes problems might come, so you have to you cannot skip this formula. Okay, next is cells in parallel. Cells in parallel I have done in Pu to Brahmastha series. You can follow that derivation, but final result is important. Derivation is slightly complicated in this. I have done a simpler version. You can check that in the Pu to Brahmastha series. You can read this derivation once, but the final result is very important. This is important as a derivation. This is important as a formula. So based on this formula, a lot of questions came in the previous year. Okay, so 1 by Req is, so you can see that resistances are connected in parallel. This is the internal resistances. So two things you have to find when the cells are connected: internal equivalent internal resistance and equivalent EMF. These two are the important things. So equivalent EMF can be written in this form. This form is somewhat simple, and you can solve a lot of problems using this form. Okay. Now Kirchhoff's rules, there are two rules. Junction rule, okay, junction rule, at any junction the sum of the currents entering the junction is equal to the sum of the current leaving the junction. It is also coming from the concept of conservation of charge. Okay, loop rule. And one more thing, this is also in most books, textbook other than NCERT, it is mentioned as Kirchhoff's current law, KCL. So if you see somewhere KCL is mentioned, that means this law. Okay, I mentioned that in my lecture, in KCET lecture. Okay, if you follow that lecture you will know. And loop rule says that the if you go through any of the given loop, any of the single identifiable loop, Okay, you start here, you can go any path, any one single path at a time. If this completes a loop, okay, then in that loop, whatever voltage drop across the resistances, if you add them everything, you will get a zero value. Okay, basically it includes the battery as well, but if you are going in the direction where battery is, suppose in this, if you are going in this direction, so battery is also sending the current in this direction. This battery is trying to send the current in this direction, right, positive to negative. So suppose you start from here and you are going in this direction. So in this case, what you can write is that the voltage drop across all the resistances equal to this EMF, or all the resistances minus this EMF equals to 0. That is also fine, but I like to simplify things instead of writing everything plus minus. Students often get confused that when to add, when to minus. So only thing you have to remember is that suppose the current in this is I, current through this is say I2, whatever value, okay, and you are using current through this is say I1, and you are going through this loop, right? If you are going through this loop, always remember that battery is trying to send the current in the same direction. So if the battery is trying to send the current in the same direction, then once you add 1 into I, 20 into I1 plus 30 into I2, okay, in that case that should be equals to 80 volts. That is the voltage of this source, right? So this is one way. You have to practice it more. I have done some problems in our Brahmastra series as well as KCET series. You can check those out, okay. And this is also called, this law is also called KVL, Kirchhoff's voltage law, and Kirchhoff's voltage law is also based on the conservation of energy. Okay, the laws are important, the statements are important, you have to remember them, you have to write them, you have to practice them, and also you have to practice the numerical question. This is one of the examples. This problem is important for competitive exams. If you are preparing for any competitive exam, especially for KCET exam, okay, this question has asked once or twice. In JEE it used to come, but now it is very common. Students nowadays remember the value and answer this question, okay. So that's why this question is no longer asked. It is 5 by 6 into one of the resistances. So students remember the value and answer this question. So that's why it is no longer asked in JEE exam, okay. Now what else? Next is Wheatstone bridge, another very important derivation. This is derivation numericals in terms of numericals, in terms of derivations for JEE, for KCET, for your PU board, okay. This formula, this derivation I have done again. I have done this derivation in my Brahmastra lecture. You can check that out. Also, the condition for balance means there is no current passing through this galvanometer. That is the balanced condition. So basically you can imagine that there is no galvanometer, all the current that is passing through, going through here, all the current coming here, they are going directly here. No current is passing through this galvanometer. So that is the condition of balance. So balance means this potential at this point and potential at this point are equal. So to flow current, there has to be a potential difference. If there is no potential difference, no current flows. So basically that is the condition here, right? Now a practical device using this principle is called meter bridge. So this is important for a competitive exam. So name one example or name one application of Wheatstone bridge. Meter bridge, one of the example. Post office box used to be employed during the telegraph era, okay, when you used to send messages using a device called telegraph, okay. So that time post office box was popular. Nowadays telegraph is completely obsolete. We do not need any telegraph because we can send SMS, right? Telegraph was old generation SMS and you have to pay for that. So suppose maybe some of you have practiced writing a telegram in your English test. When I was a student, it was a we have to write something, okay, in a telegram. Telegram was a you need to know how to write a telegram. Okay, the message that you sent was used to call telegram, and telegraph is the device that is used to send such messages, right? So those are nostalgic moment, but no longer used. So no longer post office box is also obsolete. Now at the end you can read the summary. At the end, this is very important from this chapter, this dimension table, okay. You have to, I have highlighted few of the quantities for which you have to remember the dimensions. Obviously current density I already mentioned. Mobility is important. Okay, drift speed is just normal speed, so it is L t to the power minus 1. So I assume that you know that, so that's why I have not marked it, but this is also sometimes may be confusing for some students. Electric field you have learned in the previous chapter as well, but this is a consolidated table for all the terms related to electric current, electric field, so you have to go through this dimension table. Okay, and if you remember one of them, you can find the other one. For example, if you remember resistivity, you can find the conductivity, which is just opposite to that. So m L cube t to the power minus 3 a to the power minus 2, it becomes m to the power minus 1 L to the power minus 3 t to the power 3 a to the power 2. So resistivity and conductivity are almost same. Okay, similarly there is a relationship between resistance and resistivity. You can calculate that there is a length extra in resistivity, there is a length less in resistance. So through that you can remember different quantities. Okay, similarly there is a relationship between EMF and resistance. EMF and voltage are same, they share the same unit. Okay, that's why their dimensions are same. Okay, I have not given you to remember any one, you can remember any one of them. Okay, so this was one of the questions I think given in your model question paper. So these are the dimensions that you have to remember. Okay, so with this note I am concluding this chapter. If you have any doubts, any questions, don't forget to mention that in the comment below. With all these things I am saying goodbye. I will be back with a new chapter on Tuesday. Till then, bye.